Hello dear student, welcome to the second lecture in tensor analysis. In this video, we will be learning about notations and conventions. We will be looking into the direct notation, indicial notation, range conventions, Einstein's summation convention, and also about Kronecker delta. Notations. Notations and conventions are mainly used to indicate or how to notate a tensor while writing or while in printing. So we need to specify some quantity such as a letter V or a letter sigma denotes a vector or a tensor in print or while writing. So we have to take in account of certain notations that we commonly use. So there are two types of notations that we use while denoting tensor, that is a direct notation and also indicial notations. Direct notations are mainly used when we are not particularly referring to a coordinate system. We know that tensors have to be projected or have to be displayed only in a coordinate system. We can talk about a tensor only with regard to a coordinate system. So we need to have a coordinate system. And several notation, different tensors will have different coordinate systems. For example, we have seen that the tensor, the stress tensor has an XYZ coordinate system. Whereas hope you've done the homework with it. We denote our electromagnetic tensor in another coordinate system, our 4 vector in another coordinate system. So coordinate systems differ with different tensors. And if we have to write or notate a tensor without referring to a particular coordinate system, then we will use the direct notation. In direct notation, it is just a symbolic representation. That is, we just say that this particular letter denotes a tensor. This particular letter denotes a vector. This is what we are just indicating, that this is a tensor or this is a vector. So it's just a symbolic representation, and we cannot do or it did not specify any of the algebraic operations that is being performed with the vector or the tensor. And the way in which we can notate a vector or a tensor in direct notation is using an underbar. We have already we already know that the direct notations using bold letters. When we write a vector, we use bold letters while print, or while in writing we use a vector with an overbar. But in tensor analysis, we specify a vector as a vector with the underbar. These are different notations. Direct notations we can use to specify a vector, and direct notations which we use to specify a tensor is by using this in a bold letter, typing the vector in a bold letter, or while in writing we can use tensor by 2 underbars. So in tensor analysis, we stick on to the underbar notations using direct notations. So vector having only one coordinate system or one linear direction is denoted by 1 underbar, and a tensor being having multilinear is denoted by 2 underbar or several underbars. And another type of notation we use is the indicial notations. And in this indicial notation we use when we are representing a coordinate, we are talking about a vector in one particular coordinate system. For example, if we are talking in the XYZ coordinate system, we can use indices, that is indexes which comes here, or in the as a subscript or as a superscript. There are different types in which we can write the indexes. We will come to that later. We will use indexes to denote their dimensionality. Therefore, mass being a scalar is non-dimensional. So in indicial rotation, it doesn't have any index, while velocity is a linear vector. So it will have one index, which denotes it have a dimensionality of 1, while stress tensor has as multilinear vector, or it's a tensor. Therefore, we have two indices which indicates that we need two basis vectors to specify one component. These three are given in the x, y, z coordinate system. Therefore, this can be indices notation. Indicial notation can be used only if we specify something or we talk about something in one particular coordinate system. If we need to change the coordinate system, we need to specify that too. Whereas in direct notation, even without specifying the coordinate system, we can talk about vectors and tensors. While during this video of tensor analysis, we will be sticking on to the indicial notations, because using indicial notations, we can talk about its operations performed on the tensor or the numerical computations using the tensor. Everything can be done only with the indicial notations. So we will be sticking mainly into the indicial notation. So in indicial notation, the indexes denotes the dimensionality of the vector or the dimensionality of the space in which this particular tensor is being talked about, and it gives the direction of the vector. And we have already learned how I and j, or the indices, gives us the direction in the last video. Now let us learn about different convention. Notational conventions are mainly used to make this writing tensors or vectors to a more simpler form. It is used to simplify the expressions, including summation of vectors, matrices, or general tensors. So we use different conventions. Consider this set of equations. This set of equation denotes a tensor. This set of equations says about a group of components, which is an n by n tensor multiplied by a vector which starts from x1 to xn. It starts from a11 to ann, giving us a particular value from b1 to bn. So while doing calculation with this particular tensor, we need to write all these equations over and over again, and this is going to be very cumbersome. So we need to find some particular way in which we can denote this as a whole, and this brings us to the range convention. We can see that all these equations are written in a particular fashion. That is, in every equation, only one index is being changed. That is, the first index is being changed. In the first equation, the index is 1, while the second equation it is 2, while the nth equation it is n. Therefore, we can replace all these using one particular letter I, and we can write ai1 x1 plus ai2 x2 up to ain xn is equal to bi, where I ranges from 1 to n, and here I is called a free index. Since I ranges from 1 to n, this particular convention is called range convention. Therefore, instead of writing n equations, we can write just one equation and say I is ranging from 1 to n, where I is a free index. So when some particular equation is denoted as this, when one equation in tensor analysis is like this, it is implied that we have n similar equations, where n denotes to the dimensionality of that space. Suppose this is being this is being denoted in an n by n dimension. This is denoted in an n by n dimensional space. Suppose it is being denoted in an three-dimensional space, say x, y, z space, then I will range from 1 to 3. That is, we will have 3 such equations. Therefore, a range convention actually helps us to reduce the number of equations. So when you find some equation like this, it denotes that we have n equation where n denotes to the dimensionality of that vector space, whether it is 3 vector space or a 4 vector space. Now, we already compressed our equation, set of equation to this. While writing this is also going to be a bit cumbersome when we have a long derivations. So, we need to find another way to compress this equation also. So, this equation come as a linear sum of lot of quantities. So why can't we just use a summation index and say summation j is equal to 1 to n aij xj is equal to bj. Then all these equation will get compressed to one particular equation. And the Einstein convention says that we can also drop this summation symbol. We can also drop this summation symbol and just write this. And using Einstein summation convention, we can write this whole equation as aij xj is equal to bj, where summation from j is equal to 1 to n is implied. That is, when you come across such an expression anywhere in the tensor analysis, you have to keep in mind that there is a summation symbol j is equal to 1 to n, where n denotes the dimensionality. If it is the 3-dimensional space, then n is 3. If it is a 4-dimensional space, then n is 4. Therefore, when you come across some expression like this, you have to keep in mind that there is a summation which is implied, which is not written but it's implied, and the summation is from 1 to n, where n is the dimensionality of the space. We have already told that I is the free index, and here we have another index, that is j, and j is the dummy index, and the summation is carried over this dummy index j. That is, I remains as the same and the summation is carried over the dummy index j. And the dummy index is the index which repeats in a symbol group. We have two different groups here. One group is aijxj and another group is bi. So the terms which are written as a product or written as independent are called a symbol group. This forms bi forms a symbol group, aijxj forms another symbol group. If some index is being repeated in a symbol group, then that index is called a dummy index. That is, here you can see that I is not repeated. So I is a free index, whereas j is repeated, therefore j is a dummy index. When you find a dummy index, you have to keep in mind that a summation is being implied, where dummy index changes from 1 to n. So we have find out a way to write very long equation in just 1 or 2 terms. So we have to keep in mind certain rules while doing this summation conventions. The first is any repeated index, that is when an index is repeated twice, that the term have to be summed over. See here, this is a we have already talked about the symbol group. Here we have a symbol group, and here j is repeated, and j is repeated twice, so j is a dummy index. We do not have a free index here. So if you find a dummy index, if you find an expression like this ajxj where j repeats twice, then it implies that this expression is equal to sigma j is equal to 1 to 3. If the dimension of the space is 3, then it is sigma j is equal to 1 to 3 aj xj, and that will give you a1 x1 plus a2 x2 plus a3 x3. That is, when you come across a term aj xj, you have to keep in mind that it denotes a sum of terms a1 x1 plus a2 x2 plus a3 x3. The second rule is dummy index can be replaced with any other index other than the free index. See, we can write a product group as aij xj. And when you ask me, can I replace j with any other letter? Yes, you can replace j with any other letter and say I can write it as air xr or aip xp. But you cannot write it as aii because I here is a free index. When I repeats one more time, then it will become a dummy index. So dummy index and free indices cannot be switched. So we can replace our dummy index with any other index other than the free index. So free index is a term or the index in the term which is not summed over. It appears only once, while dummy index appears twice and it have to be summed over up to the dimensionality of the space. No index can appear more than twice. We have said that the index which appear once is a free index, index which appear twice is a dummy index, and no index is allowed to appear more than twice. So if some index appear more than twice, it sometimes indicate that we have done something wrong, or sometimes indicate that it can be reduced to a simpler form where an index do not appear more than twice. Indices can be written as subscript or superscript and it is counted together. We will come to the spaces which when we write the subscript and superscript. Just for the sake of this video, you can just say that the indices can be written as subscript as well as superscript, and these indices are counted together. That is, in this symbol group, I appears once and j appears twice, not once. J appears twice. You have to count all the indices, whether they are subscript or the superscript. It have to be counted as together. So here I is a free index where j is a dummy index. Similar example, if I write aj j, that is a with j in a subscript and j in a superscript. Here also j is a dummy index and not a free index because j appears twice. When you find a dummy index, what you have to do? You have to sum over. When you find a dummy index, it is implied that you have a summation symbol here and the summation varies from 1 to n. In an equation, the free index and the dummy index of each symbol group, the free index have to match with the symbol group. Hope you remember we have how we have done dimensional analysis while we are in 12th or 11th. Similarly, when you have to equate some products or equate some tensors, keep in mind that when you have to add two tensors, then the product group should have the same free index, and also when you equate something to another, then it also should have the same free index. Here I is the free index, whereas here I appears once, k appears twice, j appears twice. So I is the free index where k and j are dummy index. In this term, I appears once, j appears twice. Therefore, I is the free index where j is the dummy index. Here you can see that free index of the first product term symbol representation, that of the second representation and that of the third representation matches. I is the free index in the first, second and the third symbol group. Therefore, this equation is possible. So, when you write an equation, the free index of each symbol group must match. Now, let's do this. This is a simple example of how we can apply this. So, using the first, we have AIXI. So, as I have said, when you encounter a term like this, you have to find the dummy index and the free index. Here, I appears twice. Therefore, I is a dummy index. And there are no other indices which appears one, therefore we do not have an free index. Therefore, AIXI implies that summation I is equal to 1 to 3. Suppose I am doing it over a three-dimensional space, AIXI, and this is equal to A1 x1 plus A2 x2 plus A3 x3. And this is how we are going to do this. Now, see the second equation. Second term, AJ xj, Aij xj. And here, I appears once, which denotes that I is a free index, and j appears twice, denotes that j is a dummy index, and both I and j will range from 1 to 3 in a three-dimensional space. So, here I ranges from 1 to 3, which denotes that we will have 3 equations, and j ranges from 1 to 3 denotes that every equation will have 3 different terms. So, we can write A11 x1, choosing I as 1, A11 x1 plus A12 x2 plus A13 x3. The another equation, another set when I is equal to 2 is A21 x1 plus A22 x2 plus A23 x3, and for I is equal to 3 we have A31 x1 plus A32 x2 plus A33 x3. So, hope you have understood the difference between a free index and the dummy index. Here we had only a dummy index, so just one equation with 3 different terms. Here we had a free index as well as a dummy index. So, we have 3 different equations with each terms having 3 different terms. Let's do another exercise. And here the exercise says find if the expressions are valid or not. And we have given with 4 different expressions. Let's check with the first expressions. Here in the first expression, we have I appearing twice. That is, I is a dummy index. Also, we have j appearing twice. So, j is also a dummy index. And this does not vary anything and it's fine. Also, we can check if any any index appear more than twice. No index appear more than twice, and every rules are followed out here. So this term is possible. This is valid. Let's check the second. Here we have 2 different symbol groups. with an equation sign. When we have an equation sign, the free indices on the right side should match with the free indices on the left hand side. So the free indices on the right hand side, on the LHS, we have free indices I and j. Here I appears only once and j appears only once. So both I and j are free indices. Let us check if both I and j are free indices in this symbol group also. Here we can see that I appears once, k appears twice. So k is a dummy index. L appears twice. So L is a dummy index while j appears once. So in this symbol group also I and j appears only once, and the free indexes in the LHS and the RHS matches. Also we have k appearing only twice and L appearing only twice. So no symbol group indices is repeated thrice. So this is also possible and this is a valid expression. Next, check the another expression, sigma ij. Here using sigma ij, we have I and j both are free indices. So let us check. Here I is a free index, j is a free index because they appear only twice, while k is a dummy index and L is a dummy index because they appear just twice, and no indices is repeated thrice. So this equation and expression is valid. Now let's check the last expression, alpha k. Here we have only one free index, that is k. Here this term should have only one index k, and this should also should have one free index k. So let's check the first symbol group. In the first symbol group, I appears twice, it's okay, it's a dummy index. J appears twice, it's okay, it's a dummy index, and k appears once, yes, it's a free index. So here also the free index is k. Let's check the another symbol group. Here I appears twice, yes, it's a symbol, it's a dummy index. J appears twice, is a dummy index. K appears once, yes, it's a free index. L appears twice, it's a dummy index. But M here appears once, so M is also a free index. But this does not match here because we have only one free index here and one free index here. So this expression, this particular expression is not valid. Hope you are clear with how we check the validity of an expression. The second next problem we have to do here is find the free and dummy indices. So when you have an operation like this, unlike in linear algebra, when you open all the bracket and plus the put the plus sign all over, this is not possible in the multilinear algebra, that is in tensor analysis. So we will check the dummy index and free index in different symbol groups. So we have the first symbol group, say AIJBI. In this first symbol group, I appears twice whereas J appears once. Let's check the next symbol group, AIJCJ. Here I appears once whereas J appears twice. Next symbol group, AIJDK. Here I appears once, J appears once, and K appears once. So when we look into this equation as a whole, we will take the highest number. Using the highest number, we can say that I appears twice, J appears twice, whereas K appears once. So in this particular expression, K is the free index and I and J are the dummy indices. Hope you are clear with this idea. We cannot get the associative property here because we are dealing with the multilinear algebra. We have to look into each symbol group in separate and take the highest number of terms an index appear. Here k appears only once, therefore k is the free index, whereas I and j appears twice, therefore they are dummy indices. Now we will move on to the Kronecker delta. We are familiar with Kronecker delta and we have done many equations using this. So Kronecker delta is denoted by delta ij, and this denotes that delta ij takes a value 1 only if I is equal to j, and it's take a value 0 when I is not equal to j. And the Kronecker delta can also be written as delta ij also. This is also the same. It can also written as a subscript and a superscript. So delta ij or delta ij both in the subscript is denotes that it has a value 1, takes value 1 only if I is equal to j. Now using the summation notations, you can see that delta ij has two free indices I and j. Suppose we are doing this in a three-dimensional space, then we will have different terms. We will have 9 different terms possible here, starting from delta 11, delta 12, delta 13 up to delta 33. We have 9 different terms possible. So in these 9 different terms, only delta 11, delta 22 and delta 33 will give you an answer 1, whereas all other terms delta 12, delta 13, delta 23, delta 21, delta 31 and delta 33 will give an answer 0. So this is how we talk about Kronecker delta in terms of tensor analysis. Kronecker delta has different uses. We use Kronecker delta in tensor analysis. In linear algebra, the Kronecker delta actually denotes, in multilinear algebra also, Kronecker delta denotes an identity matrix. That is, when ij is equal to 0. We can write this delta ij as a matrix. We have seen that all tensors are denoted by a matrix. Here delta ij can also be written as a matrix. When we write delta ij as a matrix, only the terms with the same indices 1, 1, 2, 2, 3, 3 gives us 1, and the all other terms will go to 0. So here we get an identity matrix. So just remember, when you come across a tensor, say aij is multiplied by delta ij, it just says that the matrix, in matrix notation, the matrix of the components of A is multiplied by an identity matrix, and it doesn't change anything. So it actually tells us, so linear algebra, in linear algebra, identity matrix is denoted by delta ij. The second use is dot product of any two vector can be represented using delta ij. Suppose I have a three-dimensional space with its unit vectors denoting E1, E2 and E3. Then we know that E1 dot E1 will give us 1. Similarly, E2 dot E2 gives us 1 and E3 dot E3 gives us 1. Whereas all other combinations such as E1 with E2, E1 with E3, E2 with E3, E2 with E1, E3 with E1 and E3 with E2 will give you 0. Therefore, this also, here we have three different terms, and this is one only if both I and j are equal. Therefore, product of two basis vectors can also be denoted using delta ij symbol. The next is differentiation of a vector or a tensor with its own components can also be denoted using the delta ij symbol. Suppose we have an equation x1, x is equal to x1 a1 plus a1 x1 plus a2 x2 plus a3 x3. Now the term x1 will not have any component along the direction xj, or suppose we are talking about a three-dimensional space with dimensionality x1, x2 and x3. Now x1 do not have any component along x2, so x1 cannot be differentiated with respect to x2. Similarly, x1 cannot be differentiated with respect to x3. x1 can only be differentiated with respect to x1 only. Therefore, dou xi by dou xj will give you a delta ij. That is, only dou x1 by x1 stands and all other terms take you to 0. While talking about these two, hope you have a glimpse of idea what we have done during our Hamiltonian mechanics lecture. We have done this in Hamiltonian mechanics while we are learning the canonical Poisson brackets. Hope you remember what we were doing in canonical Poisson brackets and what we used to differentiate this using different terms. So this actually comes in our Hamiltonian mechanics as canonical Poisson brackets. It's the same thing over here represented mathematically. So differentiation of a vector with its own components is denoted by a Kronecker delta. Similarly, in case of a tensor, here we have two different linear directions because it's a multilinear element. So we can differentiate the component of a tensor with respect to its own components, and this will give you only one only if these two components are equal. That is, when aij can be differentiated only with aij. Therefore, I should be equal to k as well as j should be equal to L. Therefore, we can write, it can be written as a combination of two Kronecker delta because I have to be equal to j and k have to be equal to 1. Then only this equation will give you 1. In all other cases, this equation is gonna give 0. Therefore, these are the uses of Kronecker delta. Let's do some exercises with it. So, the first term here. Here we have I twice. So, I is a dummy index and j is a free index. This denotes that we are going to have three different equations. Here j is the dummy index. So, it is a1 delta 11 plus a2 delta 21 plus a3 delta 31. Next equation is a1 delta 12 plus a2 delta 22 plus a3 delta 32, and the third equation a1 delta 13 plus a2 delta 23 plus a3 delta 33. Using the properties of Kronecker delta, we can get rid of all these terms here, and what remains is just three different terms, and that is a1 delta 11, a2 delta 22 and A3 delta 3 3, and delta 1 1, delta 2 2 and delta 3 3 will be equal to 1. So the terms which remains are A1, A2 and A3. Therefore we can write this equation as AI, or we can write it as AJ. Therefore AI delta Ij is equal to AJ. So when you have a delta Ij symbol here, then it is okay to replace this I with J. So we can use the same method here. Here also we have J is the dummy index, whereas K and L both are free indices. So we are going to have a set of equations, 6 sets of equation. From this we can come back, reduce to the terms. So I suppose you write these equations. Here when you come across a symbol delta Lj and here you have a j, it is okay to replace this j with L, and this simplified form will become ALK. And when you expand this equation also, you are going to get the same. And here you have delta IP, which is being multiplied with CIJKL. Therefore I can be replaced with P, because I is equal to P. Therefore I can be replaced with P, and the equation becomes CPJKL. So in general, if you have a tensor of n dimension by I to Z, and it is multiplied with a Kronecker delta IP, then it is okay to replace the I with P, and the equation will, the tensor will remain the same. Now for a practice, I request you to pause the video and take down these equations and try this equation. We have 3 inequalities given here. These are inequalities which are mainly used. We use these for theorems also. So it is good to remember these inequalities as well as equalities in case of we are using this commonly when we are using tensor analysis. When we go to higher order tensors, we have to use these type of equalities and inequalities there. So I ask you to open these equations and inequalities and find they are not equal. As I have already said, Aij multiplied by xiyj cannot be equal to aijxi plus aijyj, because in multilinear inequalities, in multilinear directions, it is not okay to say that these are equal. And also you can see while opening the brackets, I request you to do this exercise. Compute this, add them both and find if it's equal to this. Similarly, compute these two separately and find if they are equal. Okay, here I can say that see, I appears twice in the first term. So I is a dummy index. Here j appears twice. J is also a dummy index, as we have done in the previous example. But see here, j appears only once. So here j, we have j as a free index, and here I appears once. So we have I as a free index. Whereas in this term, both I and j are dummy indices. So this equality doesn't hold. Here also xij, xiyj cannot be equal to xij, xj, yi, because as we know, this term a1 2 cannot be equal to a21. Similarly, xiyj cannot be equal to xjyi. That is, say xy cannot be equal to yx. This is the case over here. You can find by opening the brackets. Similarly, you can see the terms here also. Here, when we multiply this over these terms aij plus aji with xi yj cannot be the same. When you multiply, this will give the free index and dummy index to be the same. But in this case, say this is equal to twice aij xi yj only if ij is equal to aji. But this is not true, because a12 cannot be equal to a21. Similarly, we have equalities also. You can see that equalities are just contrary of what we have done with the inequalities. So just find how we can manipulate it. Similarly, here you find the equalities also. Just try this using opening the brackets. If you are stuck with something, please come to me. Also, please identify the valid expressions here. I have given several expressions using the rules and the notations. Just find which of these expressions are valid. So these are my references. Thank you.